This video will discuss the critical point of gases. For an ideal gas, we saw that we obey the ideal gas equation, PV bar equals RT, or PV equals nRT. So we get that the pressure of an ideal gas is equal to RT over V bar, gas constant times temperature divided by the molar volume. So volume divided by number of moles. So if we look at the following, if we look at the derivative of the pressure with respect to molar volume, so we just take dDV of this expression, we get minus RT over V bar squared. So notice that that's an expression that as we increase the molar volume, the pressure is always decreasing. It's decreasing monotonically and steadily, and it never equals zero. There's never a point where increasing the molar volume doesn't increase. Increasing the molar volume does not decrease the pressure. That is always the case. It always does decrease the pressure. Similarly, if we look at the second derivative of pressure with respect to molar volume, the acceleration or the curvature of that slope, that's equal to the second derivative of RT over V bar with respect to V bar. That's 2RT over V bar cubed. Once again, that is never equal to zero, so it's always concave upward, always has a slope which is increasing over time, becoming less negative over time, or over as your molar volume increases. And so the result here is what we're going to see down below is that the fact that there's no interactions in the ideal gas means that there's going to be no opportunity for it to liquefy. So the gas is not going to attract itself and become liquid at any point because there are no interactions in an ideal gas. So now by contrast, let's look at a van der Waals gas. So P plus A over V bar squared times V bar minus B equals RT. If we solve that for pressure, we get P equals RT over V bar minus the parameter B, the effective molecular size, minus A over V bar squared, A being the parameter for the attraction strength between the molecules. The first derivative of this expression with respect to molar volume is equal to minus RT over V bar minus B squared plus 2A over V cubed. So there is some point where this is going to equal zero. So that's of note thus far. And the second derivative of pressure with respect to molar volume equals 2RT over V bar minus B cubed minus 6A over V bar to the fourth. So once again, there is a point where this is going to be equal to zero. So that's not true for all temperatures. So for a large temperature like T4 here, which is greater than these other three temperatures, it is pretty much just monotonically decreasing. But once we get the pressure low enough, this Tc here, we get a point where the first derivative is equal to zero. And then it goes down. But for these even lower temperatures here, like T2 and T1, if you follow the dotted line that continues here, there would be a point where the pressure would reach a minimum and then it would start going up with volume and then reach a maximum and start going down again. It would have kind of this inflection in the middle there. So this brings up a concept called the critical point. So where the first derivative of the pressure with respect to the molar volume is equal to zero and the second derivative of pressure with respect to molar volume is equal to zero, that's called the critical point. So that's our critical temperature is Tc here. That's the temperature at which this occurs, where we have the first derivative is equal to zero and the second derivative is equal to zero at our critical point, giving this type of behavior here. So the molar volume at which that occurs is the critical molar volume, the pressure is the critical pressure, and the temperature is the critical temperature, Tc. So what we have there is at temperatures lower than the critical point, what's going to happen is there's going to be a liquid phase that develops. So instead of following this behavior where the pressure goes to a minimum and then it increases with the molar volume, what we instead do is draw a line here and we connect it from this side to this side. And what happens is as the molar volume starts decreasing, we have our gas, and then our gas keeps compressing and compressing and compressing. And at a certain molar volume, the gas stops, it stops going up in pressure and it starts liquefying. So in this region in here, inside this light blue parabola, we have the gas is transferring from being a gas to being a liquid. So it starts off at 100% gas here and then goes to being 100% liquid here, and then it continues going up more quickly, the pressure going up more quickly with the decreasing molar volume. So over here we have all liquid, over here we have all gas, and in the middle here we have liquid plus gas. All right, similarly at lower temperatures we encounter a similar thing. Our pressure goes up, reaches some value, and then stays constant as we liquefy all the gas, and then it starts going up again. The value at which this occurs is dependent on the point at which the integral below and above this curve is equal for this state here. I'm not going to go into the details on that, but just note that it's where the integral of this, or the magnitude of the integral below this curve is equal to it above this curve inside this parabola here. Okay, so these critical quantities, based off of where these derivatives have to be zero, this implies certain choices for what the values of A and B are relative to these critical quantities. So you can actually derive using these expressions and using the fact that this is the critical temperature, volume, and pressure at which this occurs, that you can say that the critical molar volume is equal to 3 times the B parameter in the van der Waals equation of state. The critical pressure is equal to the A over 27B squared, and the critical temperature is equal to 8A over 27B times R. So each gas has a unique value of what this critical point is. They have a unique value for all 3 critical quantities. So these critical quantities are what are actually used to parameterize A and B. So knowing the 3 of these, we can derive the values of A and B that result. So the van der Waals equation of state is entirely specified by what these 3 critical quantities are for a given gas, which all depends on the interactions that occur in that gas, giving unique values for these critical quantities and unique parameters for the van der Waals equation of state.